So good evening, everyone, and welcome to our Wednesday seminar. So today we have our own Dmitry Blinov. A few words about Dima. So Dima obtained his master's and PhD from the University of St. Petersburg, Russia in 2011. And he stayed there for a while for a short postdoc, and then he joined the Crete Astrophysics group in 2013, and he's been here ever since. And since 2017, he's working for the Pacify project, and he's really the soul of the Robopol instrument at Skinaka. So today he's going to talk about one of the largest observing programs with Robopol at Skinaka. So Dima, thanks a lot for the offer, and the floor is yours.
Thank you, John, for the introduction, and thank you for giving me time here. Last year, we finally managed to release our monitoring data from this program called RoboPol. So I thought it's a good time to look back and see what are the results of the program and to make a little summary. So I made this talk, and I thought some of you may be interested to see this presentation. Okay, so I will talk about Blazars. And Blazars are a subclass of active galactic nuclei where we look almost along the relativistic jets. And for this reason, what we see at low energies from radio to UV or to even to X-rays in some cases is a highly relativistically amplified, relativistically beamed synchrotron emission of a jet. Aside from this low energy synchrotron peak, there is also a secondary peak in the SEDs of Blazars. And that part of a spectrum is much more poorly understood than the synchrotron emission. And it was even worse if we look back 10 years ago or something around that, when NASA launched Fermi, which is a space gamma-ray observatory that obtained, for example, this image, this full sky map of a gamma-ray sky. And what we see here, almost essentially all these point sources here, or something like 85% of them, are Blazars. And that time, around 10 years ago, when Fermi was launched, it started providing an immense amount of gamma-ray data for hundreds or even thousands of these kind of Blazars. But it was very poorly understood how these gamma rays are produced in these kind of sources. So there were very much different models. A few papers aside here, there were models explaining the gamma rays by some processes in the broadline region in a very vicinity of a black hole, less than 0.1 parsec from a black hole. On the other hand, there were other models saying that no, gamma rays are produced by a different process somewhere like tens of parsecs down the jet. And there were good observational arguments for both of these, for all these models. And then around 2010, in these two papers was emphasized that it looks like, at least in some cases, gamma ray flares like these ones here or this one here, they seem to be coincident with these kind of events called EVPA rotations, like this one here or this one here. So these EVPA rotations, or I will also call them optical polarization plane rotations, are events where the plane of oscillation of the electric vector in the electromagnetic emission starts smoothly changing the direction. And sometimes these kind of rotations can reach hundreds of degrees. In this particular case, it was 2 entire circles, right? And first event of this kind was reported in this paper by Kikuchi et al. In 1988, but since then, till 2010, there was essentially no attention paid to this phenomenon. And then after these 2 papers, it was understood, okay, if we study these rotations together with the gamma rays, probably we can get some clues about how the high energy emission is produced. But unfortunately, at that time, it was unclear how these rotations are produced. So for example, here I list a bunch of possible models. And if you have a look into these papers, you will see that these models are very much different in the physics behind this. So it probably tells us that that time we were totally far from any understanding of how this phenomenon of polarization plane rotations in blazars is created. What is the physics behind it? So this group of people, that some of the names you may recognize, decided, okay, let's look at these two poorly understood phenomena together. So the gamma ray flares and the polarization plane rotations in the optical. And let's at least try to understand whether they are related statistically and if there is some common physics behind these. And we decided to establish this collaboration called RoboPol and start this project that has the same name with two main objectives in our mind. First is to observe a large, statistically well-defined sample of blazars in linear polarization with high cadence, and then to apply rigorous statistical methods to identify this kind of polarization plane rotations in our data and to study how they are related, how they are connected to gamma ray flares, right? And we were lucky to get time for this project at the 1.3 meter telescope of Skinnekes Observatory. So we secured 4/7 of the time for 3 years, or to be more precise, for 3 seasons. Then we built a dedicated polarimeter that was specifically made for this telescope and for this project. And then we also made a control system that was to a large extent was automatic and was simplifying the operations and observations and processing of the data. And the main feature of this polarimeter, that is also called RoboPol, is this polarizing assembly, how we may call it, which is made of 2 half-wave plates and 2 Wollaston prisms. And this set of elements, what it does, it splits any incident ray into 4 rays with different polarization states. So if you measure photons in couples of these rays and do this simple math, you immediately get the relative Stokes parameters Q and U that uniquely describe the linear polarization. Plus, if you measure some of these counts of photons in all 4 spots, you get the total intensity that can be calibrated if you have some stars with known magnitudes in the field. So you can get count for your source in absolute units like millijanskis or magnitudes. So this polarimeter is, shortly speaking, is accurate, fast, simple in operation, and it has stable instrumental polarization that can be addressed with observations of standards. Okay. Another important feature of our approach in this project is that, unlike in many other monitoring programs in the optical polarization of blazars, we made our observing sample in a statistically well-defined way. So there are many other programs that picked up the most variable, the brightest sources in gamma rays and observe only those. So if you ask them, what is the average polarization of a gamma ray loud blazar in the optical, they cannot tell you because their samples are very much biased in the sense of properties of these sources in gamma rays. We instead started from a complete sample of gamma ray bright blazars and then applied a set of cuts that are unbiased, non-biasing cuts in the sense of gamma ray properties, and ended up with an unbiased sample of gamma ray bright blazars. And then we also established a set of blazars that have all properties similar to gamma ray bright sources, but were not detected in gamma rays at that time. also applied a set of non-biasing cuts and also established a control sample of Gammaray faint blazars. Okay. Okay. On top of that, we also added these high interest hand-picked blazars, but they were not considered in any statistical analysis, and that I will report later. So during this process of the sample creation for the monitoring, we had to introduce this brightness optical magnitude cut. But since we had only historic data for many blazars that were obtained some dozens even years ago, so we had to perform a single epoch survey before we start monitoring in order to get the current value of magnitude for each blazar. And right after performing this one month survey, we got our first result within this RoboPol program. And this result is that Gammaray loud blazars are significantly more polarized compared to their Gammaray quiet counterparts. So we found that average polarization for Gammaray loud is 6.4%, and for Gammaray quiet is 3.2% in the optical polarization. And these two numbers are significant, are different at 3.5 sigma significance level. And later, this result was confirmed when we averaged data after 2 years of monitoring for each blazar. We averaged polarization, and we again found very similar result that Gammaray loud blazars are much more polarized than Gammaray quiet, and this time it was more than 4 sigma significant. So immediately here we get this first scientific result that the optical polarization properties and gamma ray properties are related. So our interpretation here was that in gamma ray loud blazars, the magnetic field is more coherent, more aligned compared to more turbulent magnetic field in the gamma ray quiet ones. And later we used this property of gamma ray loud blazars for this little side project. The results of this project were published by Nikos Mandarakis in this paper. So we demonstrated in this work that optical polarization is a really good tool when you start searching for identified low energy counterparts of gamma ray sources. So the problem can be demonstrated in this sky plot. If you now take the latest version of the Fermi catalog, you will see that there are 5,000 sources there. And around a quarter of those sources are unidentified. So we know that the gamma ray emission comes from somewhere here. So these are uncertainty ellipses of the gamma ray source position. But within 3 sigma uncertainty ellipse, for example, there are dozens or sometimes hundreds of optical sources and sometimes several radio sources. So it's very hard to say which of these sources is actually related for the gamma ray emission, is actually responsible for the gamma ray emission. And now, since we demonstrated that blazars are so highly polarized on average, especially those blazars who emit in gamma rays, then it's reasonable to suggest that if you measure polarization of all these hundreds of optical sources here within uncertainty ellipses, you expect that if there is a blazar here, you expect that it will pop up in polarization, right? And then we actually performed a Monte Carlo simulation using our data and using reddening maps for the entire sky. And we demonstrated that for most of the sky, if you step away from the galactic plane, something like 10, 15 degrees, you are essentially always in this regime when your interstellar polarization is less than 1%. So your blazar should pop up among the field stars in polarization, something like in 70 to 90% of cases, right? So it should be very efficient to do this exercise to search for highly polarized sources in the fields of unidentified gamma ray sources. And we have actually done a test. We took RoboPol and went and observed 4 unidentified gamma ray sources. And in one of them, we found this faint star-like object of 17.6 magnitude that had 5.2% polarization compared to all these field stars that had less than 1% on average of polarization, right? And then we took a spectrum of this source using the same telescope, and we found that it's indeed an extragalactic source with this redshift. And we also were able to classify it. It turned out to be a complex object made of an AGN and a star-forming host around it. And probably that's why it was never identified as an AGN before, because it had very peculiar colors, typical for AGN, right? And then one last thing to say here is that when we published this paper, our source was somewhere here between 2 and 3 sigma uncertainty ellipses of this Gammaray source. But then a year later, 4FGL was published, and actually this Gammaray source moved in our favor. So now our source within 1 sigma uncertainty, and it's one of the 2 most probable counterparts for this Gammaray emission. Okay. But now let's return back to the main monitoring program results. So in this paper by Angelakis et al., we not only demonstrated that Gammaray bright and Gammaray faint sources have very different optical polarization, but also found these 2 dependencies that I think are interesting to mention here. So on the left here is the dependence of average polarization of a blazar on the location of its synchrotron peak in frequency. So you see that low synchrotron peak sources here, they have larger spread and they reach higher optical polarizations compared to high synchrotron peak sources. And something similar we observe here when we start talking about position angle. So this is chi-square. It's a quantity that characterizes how much the distribution of a polarization angle deviates from a uniform distribution. So the smaller the value, the more uniform the distribution is. So what we see here, despite of this large level of noise, we see some trends that low synchrotron peak sources, they tend to have more uniform distribution of polarization position angles compared to HSP sources who tend to have a preferred direction of polarization, right? Like here or here. So the interpretation of these 2 dependencies was also given in this paper, is that we observe in a fixed band in the optical, and when we observe low synchrotron peak sources, our band is located somewhere here on the right-hand side from the synchrotron peak. And the emission here is produced by the most energetic electrons in the jet that were probably recently accelerated by some process, whatever it is, some magnetic reconnection or shock waves. And this presumably happened in some small region in the jet, and probably during this acceleration, the magnetic field, the local magnetic field was altered and disturbed somehow. That's why we see a wider distribution of possible position angles in polarization, and also a wider distribution of polarization degree. On the other hand, in the high synchrotron peak sources, where in this regime on the left-hand side from the peak, so this emission is produced by the electrons that already lost some of their energy, and they presumably feel a larger volume in the jet somewhere downstream from the disturbed shocked region. So everything, all the processes are more relaxed here, and what we observe is in polarization is probably arises from some global magnetic field that exists in this part of a jet. Some large-scale magnetic field that is more stable. That's why we see some particular direction of a polarization that is related to this magnetic field that is stable, and that's why we see more stable polarization degree for these sources. Okay. Now, before we start talking about our results related to polarization plane rotations, I need to make a couple of definitions, and I need to remember about this unavoidable problem that every measurement polarization angle has this 180 degrees ambiguity. So this plane is exactly the same as this plane, right? So we cannot distinguish between these two cases. And essentially, whenever you have a set of EVPA measurements, it's not just a unique EVPA curve. It's a family, it's an infinite family of EVPA curves. And the only way to deal with this is to make your measurements frequent enough so that your source does not rotate EVPA between two measurements more than 90 degrees. So in practice, what you do, you have a set of EVPA measurements and you check this condition. If the current EVPA measurement deviates from a previous one by more than 90 degrees, then you shift it by plus or minus 180 degrees as many times as needed until you reach this difference, until this difference becomes less than 90 degrees, okay? But even this simple process can be made in practice in several different ways. For example, you can take into account this error term, or you can drop it like in this formula. And there are advantages and disadvantages in both these ways that are described in these two papers. In all these results that I will mention later, we were using this definition. And also, recently, Sebastian Kilman published this paper where he demonstrated that many of our curves that I will analyze and report this analysis later, they actually likely that significant fraction of them solves this ambiguity this way in a wrong way. So probably the 180 degrees ambiguity was solved in a wrong way. But even keeping this in mind, we will be considering all these events. We will consider in a statistical way. So even some part of this light curves is wrong. We still hope to see the correlations if they exist. Okay. So keeping this disclaimer in mind, now we assume that we restored EVPA curve properly, and then we need to define what an EVPA rotation is. And here we again have multiple choices. If you look in all papers before Robopol, reporting that, okay, this source has an EVPA rotation in some Julian date range, actually none of those papers defines what an EVPA rotation is. So we had to invent our own definition of an EVPA rotation, and it's written here. So all the results that I report later, they were obtained for this kind of definition, but potentially there were many other ways how to define EVPA rotations. So again, you need to keep this in mind, that I cannot guarantee you that any other definition of an EVPA rotation gives you the same results, okay? Now, say we follow that definition, we defined what part of an EVPA curve is a rotation, then we can define basically three main quantities: is the amplitude of the change in the angle, and the duration of this change, that gives you a rotation rate, that is in degrees per day, and also we will use the middle point of each rotation. When you start talking about gamma ray flares, you again hit this problem of multiple possible definitions what a flare is. And we again essentially arbitrarily selected one of these definitions that follows Nalivaiko 2013 paper. It's again written here. And we again arbitrarily replaced this half factor in the definition to this value, just to be more sensitive to this kind of little amplitude flares, small amplitude flares. This factor regulates you the amplitude of possible flares. Yeah, here as an example, I show a photon flux light curve for some blazar, and the red points are the flares according to this definition, right? So when you define your flares, you can fit them using, for example, this kind of function that has an exponential rise and exponential decay, and it will give you 4 main parameters for each flare. That will be the amplitude, the rise time, the decay time, and the Julian date of a peak of a flare. Okay, and now later we use all these quantities. But before that, I will show you the main result of our monitoring program. After 3 years of monitoring, we detected 40 EVPA rotations in 24 blazars that I will call rotators later. And these two numbers above, they show you how many rotations were reported in the literature before. So as you see, we increased the statistics quite a lot. And in this plot, the middle panels, they show some examples of the events of these kind of rotations. So the red points here, this is what is defined as EVPA rotations according to our definition. So in this case, this is 4 points is the minimal possible rotation. 4 points and 3 significant swings between them. And this is some other blazar. We saw 2 rotations in 1 season here. So now, just looking into these numbers, you see that 40 events happened in 24 sources. And as you may remember from previous slides, we had many more sources in our sample, right? So it looks like in some sources there are more than 1 rotation, in others there are 0 rotations. And the first question that follows is, do all blazars exhibit EVPA rotations? And in order to address this, we considered these EVPA rotations as a Poisson process, right? So that there is an average characteristic frequency of these events for a blazar. So events appear randomly and they are unrelated to each other. And in this kind of process, you can estimate using the Poisson statistic, you can estimate the probability of having n events if you observe for a period of time t, and the average frequency of events is lambda, right? So what we have done, we separated our sample in several subsamples, depending on how many rotations we have detected in the sources for these subsamples. And for these subsamples, we can estimate the average frequency of events, since we know how many rotations we detected and we know the observational window, duration of the observations. So now playing with these subsamples and these numbers, just putting them into this formula, we estimated that it's very unlikely that all blazars exhibit rotations of a polarization plane with the same frequency. And in fact, there is a subset of blazars that exhibit rotations like an order of magnitude more frequent compared to others. And then obviously we have a following question that, okay, what is so special about these blazars who exhibit rotations, about rotators, as we call them? And we demonstrated that even if you take out these rotation periods from the light curves, you still, in the remaining parts, you still have higher amplitude of variability and faster variability compared to blazars that don't exhibit rotations. We also demonstrated that these blazars with rotations were more luminous in gamma rays, and they are more variable in gamma rays. Variability indexes are higher. And then one more thing we found, that these optical polarization plane rotations, they tend to happen in low synchrotron peak sources. So this histogram shows you the distribution of our samples by class, low, intermediate, and high synchrotron peak sources. And you see that most of the rotations, they actually happened in LSP sources. And using these numbers, numbers from this histogram, you can do some simple textbook combinatoric exercise, like selecting balls of different colors and estimating the probability of having particular number of balls. Exactly the same exercise here. So we found that there is 1 or 2% chance probability of having as many rotations in LSP blazars as we see just by chance. And 1 or 2, it depends on what you consider as a parent sample, only gamma ray loud or gamma ray loud plus gamma ray quiet. So again, we see that it is unlikely that so many sources rotate, so many rotators are LSP sources just by chance. And then we can again return to this sketch from a few slides ago. And again, we can remember that in the optical, we observe low synchrotron peak blazars at this part of a SED, right-hand side of a synchrotron peak. So we observe probably the most energetic part in the jet, the most compact and highly variable parts of the jet, okay? And probably EVP rotations are related to this fact, okay? Now, what about connection between individual rotations and individual gamma ray flares? So we can discuss this connection using these plots on the left-hand side. So these are separate blazars and separate seasons of observations. The points are gamma ray photon fluxes by Fermi-Lat. The red points are the gamma ray flares following our definition. The green region is our observing season when we have optical data, and green ticks is our individual measurements of optical polarization. And the pink region is where we have EVP rotations according to our definition. So like after a short glimpse at these plots, you can see that in general, you can see that EVP rotations may more or less somehow intersect with some gamma ray flares here, probably with exception of this case. There is no gamma ray flare here, but there is a rotation. Now, if you actually calculate the time lag between the middle point of rotation and the peak moment of a nearmost gamma ray flare, you can see that these time lags essentially for all these blazars and all these events, they are consistent with zero within error bars. So this is the amplitude of a flare in the relative units versus the time lag. And with a few exceptions like these ones, or this one here, they are all consistent with zero. But what if this is just a chance coincidence? If you look, for example, at this curve, you see that essentially any moment there is some gamma ray flare. Whenever you put here some rotation, you will be probably very close to some gamma ray flare. So in order to address this possibility, is it possible that we are just accidentally small? We made exactly this kind of exercise. We made a simple Monte Carlo simulation where we dropped a random simulated rotation in these green regions for each of these cases. And then we found the nearmost gamma ray flare, calculated the time lag between the simulated rotation and the closest real gamma ray flare. And we plotted this distribution. So here there are 1 million CDFs from this simulation, and one solid black line is the real observed data, real observed distribution of time lags. So what we learned from the simulation is that only in 70 cases out of 1 million of simulations, our simulated CDF was entirely to the left from the observed one. So it means that all time lags were smaller than the observed ones. And from this, we conclude that with this small probability, we can have these time lags as small as we see them just by chance. So from this, we conclude that it's very unlikely that EVP rotations are not related to gamma ray flares. There must be, at least in some of these events, there must be some connection between them. And if this is the case, then you expect that some parameters of gamma ray flares should be somehow related to parameters of EVP rotations. And this is what we have in these plots, 2 plots on the left. So the plot on top is the amplitude of a gamma ray flare in luminosity units, yes, versus the amplitude of corresponding EVP rotation. And as you see, there is some sort of correlation here. There is a more than 3 sigma significant slope of a best fit line. And this is similar correlation. Here we consider the characteristic time scale of a flare versus the duration of a rotation in days. And we again see some sort of correlation. In this case, it's marginal significance, something like 2.8 significant, 2.8 sigma significance level. But now we can also remember that this luminosity is actually a function of redshift and Doppler factor. So we can also check this correlation between Doppler factor and the amplitude of EVP rotation. And we again see that there is a significant correlation. And then we can also remember that Doppler factor is a function of viewing angle and actual Lorentz factor of a jet. So basically velocity of a jet. And again, these both parameters, they are correlated with amplitude of EVP rotation that we observe. There is one exception here, is this source 3C371 that you see pops out from the rest of the points, just because it's a peculiar source. It's a transitional source between a radio galaxy and a blazar. So it has very small Doppler factor, smaller than 1 order of magnitude different than the rest of the sample, right? So it was not used in these fits. So plots in this slide, these dependencies, they immediately tell us, okay, there is indeed a physical connection between gamma ray flares and between optical polarization plane rotations. This is the major result of a RoboPol monitoring program. This slide I will skip. But now, when we establish that there is this connection, we are interested to say what is actually the model behind these EVP rotations. How are they produced? And it is still not so easy to say, because most of these models that I mentioned in the introduction, they successfully reproduce most of the characteristics of EVP rotations that we observe, for example, amplitudes or durations, rotation rates, etc. And they even reproduce more let's say, tricky parameters, like the one demonstrated by this histogram. What we see here is a distribution of polarization during rotation divided by polarization during non-rotating periods in the same blazar. So we see that during polarization plane rotations, the observed polarization degree on average drops. So there is this peak that is below 1, somewhere around 0.6, right? So it's not very obvious, observable, but even this thing can be easily reproduced by totally different models, like shown in these plots on the bottom. So this, for example, is a realization of a so-called turbulent emission terms. I don't remember what section. It's one of the models explaining EVP rotations made by Marsher. Turbulent emission multi-zone model. So there is a rotation here of EVPA produced in this model, and we see that on average polarization drops during this event compared to the polarization level next to it. This is second plot is a totally different model. It's 3D full MHD simulation of a shock propagating in the jet. So this model reported in these two papers by Zhang et al. And again, we have a rotation produced in this model, and we see the dropping polarization during this event. This is another totally different model. This is magnetic reconnections in the jets. Again, rotation and dropping polarization compared to non-rotating periods here and here. And this is from Sebastian's paper, where he simulated the entire set of RoboPol's rotations using a random walk model. And again, he was able to successfully reproduce this polarization drop during rotations in this simple random walk model. That is also not very obvious why it happens, but I think he has an explanation in that paper. So you see that these very physically different models, they reproduce even these kind of things. So it's hard to discriminate between these models. But fortunately, we have some even more sophisticated predictions from other models that can be tested using observational data. So this plot on the left you have seen before in the introduction. It comes from this paper by Marsher et al. 2010. It's a very well cited paper, something like 400 or 500 citations. So it's very well known in the Blazar community, but since not everyone who is listening here now is from Blazar community, I will explain you what is going on here. So we have a set of observations for this Blazar PKS 1510. We have a set of gamma ray flares here that are marked with blue lines and with numbers, and coincident in time optical flares at the same time. And what is interesting here is that if you calculate the ratio of a flux in gamma rays to optical flux, this is so-called Compton dominance, you will see that there are two populations of flares here with very different Compton dominance. So this presumably indicates you that there are two different mechanisms producing this set of flares. And then along this set of flares, there was a record long optical polarization plane rotation, and there was an ejection of a new radio node here, this node 2, and it happened exactly at the very end of a rotation in the optical. And the interpretation of all this set of events proposed in this paper is sketched in this plot on the top. So what we have here is a fast spine of a jet permitted with a helical magnetic field. And there is an emission feature propagating within this fast spine, okay? And since it traces different parts of the jet with different orientation of the magnetic field, we see this optical polarization plane rotation during its propagation. Then while it's propagating, it passes through a set of ring-like condensations in the sheath of a jet. And every time it passes through this kind of ring, photons produced in this ring, they are accelerated within this emission feature. Photons are scattered through the inverse Compton mechanism in this emission feature. So we see a set of external Compton flares when it passes through this kind of rings. And then at the end of the acceleration and collimation zone, this emission feature hits this standing shock. And at this moment, we see the end of rotation, and we see the sharp flare in optical polarization, because the magnetic field is very much compressed at this moment due to shock-shock interaction. And at this exact moment, we see a sharp flare in synchrotron, and we see synchrotron self-Compton gamma ray flare. Okay, and what is interesting here is that this paper made this very clear prediction that if this system of rings in the sheath of the jet is stable enough, then the next time another emission feature propagates in the spine of a jet, it should pass through the exact same set of rings in the sheath. So we expect to see a very similar set of gamma ray flares, external Compton gamma ray flares during the next EVP rotation, right? So pretty complicated prediction. And what we have done, we collected all RoboPol rotations, also went to the literature, checked papers in the literature, collected all those, identified Blazars where we had more than one EVP rotation, processed gamma ray data for those sources, and we found exactly what is predicted in this paper. So this is 3C279, one of the Blazars. This is already non-RoboPol data, but anyways, it was just the best example of this kind of event. That's why we focused on this source. So what we have here is photon fluxes, gamma ray photon fluxes light curve, optical magnitudes light curve, polarization degree, and optical EVPA. So what we see here is three major events that I'm emphasized by these pink regions. These are three major EVPA rotations. And now if we go and take these parts of a gamma ray curve next to these rotations, or even coincident with them, like this second one. So we take parts of a gamma ray curve between the dashed lines, and we plot them. We first of all stretch second one by this factor and squeeze the third one by this factor, like it's shown in this animation. And what we see is this pattern of flares that resembles very much the first part of the gamma ray curve, right? And I emphasize here that this part number 3, this piece of a gamma ray curve number 3, is separated from the first one by 6 years in time, and it still resembles it very much. So in this paper, we actually show mathematically that these are actually the best matches in the gamma ray curve under these stretching and squeezing conditions mathematically. So it's not only a a visual resemblance of a curve, but it's possible to prove that it's indeed the best matching pieces of a curve. So, okay, we believe that this is actually what was predicted in that model by Marshall et al. 2010. Now, if you look in this EVPA curve carefully, you can see that there are these three seasons alpha, theta, gamma, that essentially are super stable in EVPA compared especially to the three previous seasons. But this is an illusion. The thing here, what's happening here is that during these three seasons, the polarization level was very high, especially compared to previous seasons again. So presumably there is some kind of highly polarized underlying source in the jet that was producing highly polarized emission. So even if there was some activity, even if EVPA was rotating during these periods, we could not see it because all on the QU plane, all the points are shifted away from 0, 0. So even if EVPA was rotating, the rotation was not around 0, 0. So we could not, in principle, see any changes of EVPA here. But fortunately, even in this case, we can detect loops on the QU plane that correspond to EVPA rotations, and there is a special application for this. So we run our data for these three seasons for this application called time tubes, and we found this 3/4 of a loop on the QU plane. If you shift all these points, if you shift the centroid of this distribution to 0, 0, and accordingly all points, this 3/4 of a loop that is marked by orange symbols, it would correspond to 120 degrees rotation in this period of time between two vertical green lines. So there was a hidden EVPA rotation due to this constant highly polarized underlying source. And now if we take this part of a Gammaray curve corresponding to the same period, we again see a similar pattern in the Gammarays as the one I mentioned before. So we believe this is the fourth repetition of the same pattern of the Gammaray flares. Now, if you remember the paper by Marshall, there were ejections of radio nodes after each of the rotation events, and we also have them. So we go to literature, collect data on the radio nodes ejection from the Boston University 43 gigahertz monitoring program. And again, for most of our events, we have these associations. In this case, this node, in this case, number 4, we associated with C34. And for the first event, we have two possible associations. Since uncertainties are very large here, we cannot say which node was responsible for this. For the event number 2, we don't have any node, but this is presumably happening before because there were two other nodes, C31 and C32, propagating in the first mass from the radio core. They were very bright at this moment. The flux in this plot, you can see that flux of these radio nodes was several times higher than the core itself. So probably it was like outshining everything in the vicinity of the core. That's why we couldn't see any ejections of new radio nodes in this period. This is how we explain this. Now, also using kinematics data for these radio nodes, we can estimate the size of the emission zone where our repeated pattern of gamma ray flares is produced, and we found that it's 11 parsec in size. So it cannot be anything. It cannot be a broadline region. It cannot be the dusty torus. This must be something along the jet, far away from the black hole, that produces the seed photons that are later upscattered to gamma rays using through the inverse Compton, external Compton mechanism. Okay. So I hope all this convinced you that our interpretation is correct, and to convince you even more, we made this fancy animation. So you see these emission features propagating in the jet, passing through a set of rings, and every ring gives you a gamma ray flare here. And every time these nodes propagate with different speeds, we see the same pattern of gamma ray flares. Okay, I see that I approached 50 minutes. So I probably Okay, if you allow me, I can take a couple more minutes. Why is this important? What I described you, this kind of jet with a fast spine and a sheaf around it, it's also called a structured jet. Now there is a lot of discussion about neutrinos in the literature and AGN as a possible source of neutrinos. So there were many papers recently reporting some significant correlations between neutrinos arrival directions and active galactic nuclei. And on the other hand, there are like papers claiming totally the opposite, that there is no correlation at all. So it's a really hot topic now in in the literature related to AGN. Are the AGNs responsible for neutrinos or not? On the other hand, if you look at this from the theoretical perspective, there are many theoretical works that say that this kind of structured jets, as I explained, with a fast spine and a slow sheaf around it, they should be very much efficient in producing neutrinos. So this is just some example from this paper by Tavecchio, Ghisolini, and Goetta. There is some model here with two possible variations. Details are not important. What is important here, if you only have the fast spine in the jet, the neutrino production is not very efficient. But if you introduce on top of the spine, you introduce a slower sheaf, like in our model, you see that neutrino luminosity immediately increases by 2 or 3 orders of magnitude. So potentially looking for this kind of jets in gamma ray data, looking for this kind of repeated patterns may be profitable when you start looking for jets, for AGNs that should be able to accelerate neutrinos. And here it's probably by chance, but our source 3C279, where we found this structured jet, is one of the sources, one of the 4 most probable blazars, according to this paper by Plavin, as a neutrino producers. So this is one of the things we are doing, that we are going to do in future, to look for this kind of repeated gamma ray flare patterns coincident with VP rotations in other blazars. Okay. So aside from observing blazars, aside from the main monitoring program related to blazars, RoboPol was involved in many other projects, including interstellar medium analysis of how the magnetic field is operating and how it changes the interstellar medium. So there was a set of publications related to this. We have a couple of papers. The one is coming soon about gamma ray bursts. We have TD studies, we have X-ray binaries, and many others. And there will be RoboPol on steroids coming soon, hopefully, that exploits the same principle. Any incident ray is split into 4 different rays with different polarization properties. But this time, these 4 rays will be projected on different CCDs. So we will be able to study the entire field, all sources in the field. And in this case, the field of view will be much larger, will be half a degree. And the purpose why we are building this polarimeter is very different. So in this case, we will be able to clean the foregrounds and the microwave emissions. So we will probably be able, we hope we will be able to help the CMB projects that are looking for B mode polarization. And this is all what I wanted to show you. So our most important conclusion from RoboPol is that optical polarization planar rotations in blazars are indeed physically connected to gamma ray flares. And we successfully reached our goals of a project, and our data are now publicly available. Check out this paper if you want to use them. Thank you for your attention.
Thank you very much, Dima, for this nice review. The questions for Dima. I see a hand raised by Rafael. So Rafael, go ahead.
Yes, Dmitry, thank you very much for this nice
Thank you.
presentation. I would like to ask about the uh, rotations in the QU plane. So you used the QU plane rotations in order to the QU plane in order to find some hidden imprint of EVPA rotation, right?
Yes.
And my understanding is that the QU plane is superior than using the actual polarization angle.
Yes.
So have you considered in, you know, are you planning to go back into the RoboPol sampling and study the rotations in the QU plane rather than using the actual values?
Yes, yes. That's indeed one of the things that is in our mind that has never been done, is to look for this kind of hidden, as we call them, EVPA rotations that you cannot see just because there is a underlying very highly polarized source, right?
Okay.
And I think Yanis Leodakis was at some point on top of it, but I think it's not completed yet. But yeah, it could be a big study. Actually, we can find many more rotations compared
Exactly. You may
to that list of 4
increase
events.
yes.
Yes.
And if I may, one quick question about this model that you tested. Do you know what creates these stable disks in the jet?
You mean this kind of rings in the sheath?
The rings, yes, the rings.
Yeah.
Why are they stable along the jet structure?
Yeah. So there is actually a lot of related discussion nowadays, also in Blazar science, how they can be formed. So it can be some sort of wind from the disk, from the accretion disk, that forms this kind of structure, but they are not. It's hard to explain in a couple of words. It's a lot of literature on this, and it's one of the things that is actively discussed now. Yeah.
Okay.
But mechanism behind this is not clearly understood. Yes.
Okay.
There are simulations that are able to reproduce them, and but it's unclear whether the process is involved in these simulations is actually what is taking place. Okay. It's again like multiple possibilities, multiple possible models, but we cannot stop at this point and say, okay, this one is what actually works.
Great. Thank you very much. Very nice one.
Thank you.
Sorry, I was muted. So thank you, Rafael. I see the next hand is by Vincent. So Vincent, please go ahead.
Hi, yes. Thank you, Dima, for this very nice talk. I wanted to ask you if we have any clue of what this stretching and squeezing parameter can be related in the study of 3C279. I didn't get it.
Yes, it's just a fact that this individual emission features that you see in this animation, they propagate with different velocity for the jet, right? So we have different Doppler factors, and so we pass the structure with different time, right? One faster passes faster, so you see this pattern faster. So very simple idea behind it.
Okay, thank you.
Does it make sense? Is it clear? So they just emission features with different velocities propagating through this stable structure. The faster one produces faster flares. The slower one spreads it in time to longer. That's why we use these stretching factors. And we actually see this in radio too, when these blobs propagate in the jet, in the radio maps, VLBI radio maps, right? We also see that we have very much different Doppler factors. And it is consistent what we observe here in the gamma rays.
Okay, thank you. I did miss it. Thanks.
Yeah, sorry, that was my bad explanation apparently. Yeah, so this is where within the model itself that we have different velocities. Yes.
Okay, thank you, Vincent. So Mr. Gupta is next.
Hi, Emily. No, this is a very nice talk.
Thank you.
You have very nice data. I think there are, you can, if you look for the cross correlation for FSRQ in gamma ray, optical and optical flux and polarization angle. So there is a very fair chance you can get most of the time very strong correlation and sometimes anti-correlation. So did you try that?
Yeah, I think I know what you refer to. There were papers reporting this, but we have not analyzed this in any of RoboPol papers.
Okay.
But you are very much welcome to do this because all the data are public. I think at some point it was in our plans, but I'm not sure if we will ever touch this. So you're very welcome to use our data. And
Sure. I will certainly I will use that. Okay, thank you.
Okay, thank you very much. Other questions for our speaker? And okay, Rafael has a second question.
So sorry, since there is no other question.
Yeah,
Since
go ahead.
it's related with Vincent's question about this stretching. My impression is that you could use probably this duration of these patterns and estimate somehow, you know, as a proxy of the size of these rings, right?
We used to estimate the separation between the first and the last ring. Look, like let's say this is the first ring responsible for the first flare in the pattern, and this is the last one, right? So using the motion of these components in the radio that emerge in the radio later, you know their velocities, right? And then you know duration of these patterns in our reference frame. So you can combine these two things, and then you estimate the distance between the first and the last ring. And this distance is 11 parsec.
Oh, okay. But also, I guess from the actual duration of the individual events, you can probably use it as a proxy of the size of its ring within the jet.
Yeah, potentially you can consider individual flares here, sub-flares, and see how large they are. There is a lot of stuff that can be done there. Estimate, you know, luminosities of each of this ring.
Yeah, I can see. Yeah,
you can do some really numerical models there, but it was not our intention. It was just the first paper reporting that these kind of things exist.
Just as a.
But yeah, we actually hope that somebody will follow up and do some complicated modeling of this and derive some important parameters.
Nice.
Okay, so thank you again, Rafael. Any final question for Dima? So 3, going 2, going 1. No. Okay, so then let's call it a day. And for those of you who are here at the Institute, there is now cake waiting for us at the Skina classroom. So see you soon. And for everyone else, see you again soon online. So bye, everyone.
Thank you, everyone. Bye-bye.
Bye. Thank you, Dmitry.
Okay, bye-bye.